Okay. I see. So, Jihao, you are ready, right? Okay.
Yeah, sure.
Okay. So today we have the first speaker is Jihao Liu from on the way to Northwestern University, I guess. So he's talking about minimum model program for generalized log canonical pairs. Yes, please.
Okay. So maybe I'll just get started. So first of all, I would like to thank Professor Dirty Zhang and other organizers for inviting me to this talk. So today I'm going to talk about the minimum model program for generalized log canonical pairs, which is a recent joint work with Christopher Haken, which is my advisor. So first of all, I would like to give a structure of my talk. So in this talk, we just discuss the minimum program for generalized pairs, which clearly contains two ingredients. So first is a minimum model program, and the second is a theory of generalized pairs. So first, I will introduce the theory of generalized pairs, which is a technical but powerful tool introduced by Professor Picard and Professor Dirty Zhang in 2014. And then I will briefly talk about the classical minimum model program and some of its recent developments. And after that, I will mainly talk about the minimum model program for generalized pairs, which is the title of my talk today. And in particular, I will talk about my recent work with Professor Haken, which proves the cone theorem, contraction theorem, and the existence of leaves for generalized LC pairs. And depending on the times, I will talk about some ideas of our proofs that are expected to be useful for some further applications. And maybe I will also talk about some open questions. So without further notice, we will always work over an algebraic closed field K of characteristic 0. So in other words, let's just say we work over the field of complex number C. All right, so first let's define generalized pairs by Picard and Zhang. So we define this generalized subpair. So we write it in the form x comma b comma m over u. So this notation is different from some other references, and I will explain that later. So when I write this, so I assume that this x to u is a projective morphism from a normal variety to a variety. So in this talk, for simplicity, let's just assume that x and u are both quasi-projective. This is clearly a natural assumption. And this B will just be an R divisor on X, which means that it is an R linear combination of real divisors on X. And if B is greater or equal to 0, means that all the coefficients of B are non-negative, then we say that this XBM over U is a generalized pair, and J pair for short. And finally, so about this M, so this is like the key idea for generalized pairs. So we say that M will be a nav over U, B divisor over X. And clearly we want this Kx plus B plus Mx is R-Cartier. So for the audience who are not familiar with this notation of B divisors, I give a brief explanation here. So for this B divisor M, we just think that for any birational map X to X prime over U, we want to choose a representative divisor on this X prime, and we call it Mx prime. So the choice of this Mx prime is not arbitrary. So for this nav B divisor, we want to choose a nav over U, R-Cartier R divisor, Mx delta, which is over X. So here X delta to X is a birational morphism. So after we choose this NAF architecture R divisor, for any x prime, we can define this mx prime in this way by taking a common resolution, take the pullback, and then push down. So one can easily check that this mx prime, this definition is independent of the choice of w. And in particular, this mx will be the push forward of mx tilde. So if the audience is not familiar with this language of B divisors, one can just consider this mx as the push forward of a NAF over U R divisor. So I mean, so in general, this will not cause much trouble because in many situations we only consider the properties of this divisor kx plus b plus mx as a whole. So this is just the definition, but I mean, I still want to add some additional comments so that the talk will be more convenient for me to give. So first of all, we want to require this M, that model part, to have one slightly strong property. And we say that this M, we call it M is NQC over U. So what does NQC mean? So NQC means that, let's say in the previous example, we choose this representative mx delta. We want this mx delta to be a positive R combination of NAF Cartier divisors. And this is actually also a natural assumption because when this mx delta is a Q divisor, this NQC is equivalent to NAF. So here this NQC stands for this NAF Q Cartier combination. And actually, in the original definition of J pairs in the paper of Picard and Zhang, so they actually only, so their definition of Jonas pairs is actually correspond to our NQC J pairs here. So for the convenience of the audience in the rest of the talk, so we will only consider NQC J pairs. So in the rest of the talk, without further notice, when I talk about a J pair, we always only consider NQC J pairs. So if the audience is not familiar with this concept NQC, one may just think about the case when this mx delta is a Q divisor, when everything is a Q divisor and it will go fine. And so this NQC in some ways is actually important. And I want to emphasize that some results for NQC J pairs will not hold for J pairs without the NQC assumption, even for surfaces. So so there is like a very simple example which I will not give here, but it is possible for you to find a NAF divisor, a NAF R divisor on a surface and a sequence of curves such that their intersection of numbers goes to 0. So this is actually because the NAF cone on a variety may not be a rational cone. But that is out of the topic for today. So anyway, into this talk, we will only consider NQC J pairs. So the second comment here is that I want to talk about our notation. So our notation is different from the one in Picard-Zhang's paper. So it may cause some kind of confusion because actually when I write x comma b comma m over u, well, this is actually a relatively triple instead of a pair. But on the other hand, so seems like the theory of joint pairs has been developed for like 7 years, and also because it is a very technical definition. So at the moment, we feel that this might be the most convenient and efficient notation we can use. And again, we will still call it a joint pair because that is in the original definition. And the last comment is that it's a standard comment, is that when this U is just a point, they will just say that this generalized pair is a projective generalized pair. And if there's no confusion, like if when this U is not important, they may drop U and just say that this XBM is a J pair. So, I mean, like, for the second case, when U is important, when U is not important, so this usually happens when we want to consider the properties of generalized pairs in the local case, like the singularities of the generalized pair. And I will talk about that later. Okay, so is there any questions up to now? So if not, let's move on. And again, this is a technical definition, and I will just give you some intuitive examples of generalized pairs, some embryonic forms. So I will give you 3 examples. So the first 2 examples are about canonical bundle formula. So let's say X is a smooth projective variety with non-negative eta dimension. Then we can take an eta fibration of Kx, and let's say we have a very general fiber F. Then by the canonical bundle formula of Fujino-Mori, we know that there will exist a projective generalized pair, I will write it CBZM, with some additional good properties. So I will explain this in detail later, but anyway, from the construction, we know that the coefficient of this BC are always well controlled. Then in this case, when the dimension of C is positive, we will have an isomorphism on their pluricanonical section rings. If we want to multiply this Kx and Kz plus Bz plus Mc with any multiple which divides the non-binary order of Ks. So here we have a natural generalized pair structure. The second is also a canonical bundle formula. So, but this is slightly different from the previous one. So let's say we have a projective sub-log canonical pair. And let's say we have a contraction such that K plus B is trivial over the base. And again, let us assume that the base has positive dimension. Then then another canonical bundle formula, which should be proven by Ambrose and Prokhorov-Shorokov paper, we can find another generalized J subpair CBZM on the base, such that K plus B is R linearly equivalent to its pullback. And similarly, this CBZM also have some additional good properties. And one can easily find that from the construction, all the coefficients of this BC are constructed as 1 minus some log canonical circles. The last example is a so-called Kalmata's sub-adjunction formula. So there are many versions, and I will just state one of them. So let's say we have a log canonical pair, and let's say the C is the normalization of an LC center of XB with positive dimensions. Then Kalmata's sub-adjunction formula essentially tells us that we can do a junction of Kx plus B to C. And that will be R linearly equivalent to a generalized pair, Kz plus Bz plus Mc, where the CBZM is a generalized pair. And again, it has some additional good properties, like the coefficient of BC. They are also computed as 1 minus some log canonical circles. So like in all these cases, we will naturally get some journless pair structure, even if we only consider the study of pairs or varieties. So now let me emphasize, so what are these additional good properties here? So to tell this in detail, so one would like to introduce the singularities of journless pairs, which is similar as the definition when we define the singularities for usual pairs. So similarly, so let's say we start with the journless pair or journless subpair, and then for any prime divisor E over X, we can take a sufficiently high log resolution such that E is on W, and this is a log resolution of X and the support of B. And let's say that the modular part M will descend to W. So, if you're not familiar with the language of B divisors, you just think that here MW is already mass. So in this case, we can pull back Kx plus B plus Mx and get another journless subpair, W, BW, and M. And in this case, we can define the log discriminants of E respect to XBM. So I will write it as AE XBM. This will be equal to 1 minus the multiplicity of E of E along BW. So again, there are many other notations for this log discriminancies for journless pairs in different references, but I think that this notation might be the best one. So similar to the neutral pair case, we see that this journless pair is sub JLC or sub JKLT if the minimal log determinacy is greater or equal to 0 or respectively strictly greater than 0 for any E. So once we define the singularity of journless pairs, so we can go back to those intuitive examples, and we can see that all those journless pairs will have good singularity properties. So in either Fujino-Mori Bundle formula or Ambrose and Progrove-Shawcroft Bundle formula, one can prove that if we start with a KLT pair, then the journless pair on the base will be journless KLT. And if the pair is LC above, then the journless pair will be JLC downstairs. In Kawamata's journless formula, we will always have that the journless pair is JLC. And if that C is the minimal log canonical center, then this journless pair is actually journless KLT. So actually, so one can see that this by using the language of journless pairs, so one can actually describe the structure of this induced journless pairs very well. So before, like the formal definition of journless pairs by becomes Zhang. So in the studies related to these topics, so people usually need to consider like this BC as a B divisor, and in many situations, they need to emphasize and write some sentence like this. But I mean, with the language of journless pairs, I mean, such explanation can be more straightforward and more convenient. So now we have given you some intuitive examples for journless pairs. So now let's talk about like why is journless pair useful. So again, this is very technical, but at least in the following two situations, it is very useful. The first case is that when we have a favoration structure. So this is because the canonical bundle formula will automatically give us a J-pair structure. And in particular, in the original definition of journless pairs, Picard and Zhang used this philosophy to prove an important case of the effective Ithaca favoration I think it's not structure, but should be conjecture. And one special case for this philosophy is that for any log-canonical log-cardinal pair with non-empty boundary, so let's say that it is Q factorial, then we can always run a KX MMP. So KX is not pseudo-effective, so it will terminate with a more. So let's say we run a KX MMP with scaling of an ample divisor. Then it will terminate with a more irretrievable space, such that either dimension of V is 0, in this case, X prime is of picker number 1, which is good for us, or we will have such a canonical boundary formula and get a Journalist pair downstairs. And you can see that in this case, this Journalist pair, KZ plus BZ and plus MZ, so this is also like a so-called generalized log-cardinal pair. So this is also numerically trivial. Yes, so KZ plus BZ plus MC is also numerically trivial. And this strategy will be very useful in the study of log-cardinal pairs. And the second case is when we have a natural choice of a NAF divisor. So this includes, but will not limit to, the case when we consider varieties with anti-NAF canonical divisors. And in particular, like for file type varieties, and actually in Because proof of the BAB, he actually used this philosophy. And actually, this philosophy is very similar to this log-cardinal case. So the log-cardinal case, we actually have an anti-effective canonical divisor, and here we have an anti-NAF canonical divisor. So these two cases are very similar. But in the last case is on the minimum model program. So this is because once we have a minimum model, the canonical divisor will be NAF. And therefore, one can use this philosophy to prove the termination of pseudo-effective flips in dimension 4. So there are many references on this topic, and I will just give all the references here in these 4 papers, and see also these 2 papers. So, okay. So in the rest of this talk, I will emphasize the last part, the minimum model program for Journalist pairs. So I have already explained why the Journalist pair is important for the minimum model program. But now I would like to explain why the minimum model program for Journalist pairs is important for the minimum model program for usual pairs and varieties. So I will cover this by giving a structure, an idea of the proof of termination of flips for pseudo-effective pairs in dimension 4. So for simplicity, let's say we start with a smooth projective variety X of dimension 4, or one can also think that X has KRT or log canonical singularities. So we already know that X always has a minimum model X prime, but this is not enough for us to prove the termination of all the flips. But anyway, as we have such a minimum model, we have and we automatically have a NAF-B divisor, which was which descends to X prime. It's just so let's just say the B divisor corresponds to KX prime. And therefore, for any sequence of flips, we can consider such Journalist pairs where the Ti is the Journalist log canonical threshold. And one can check that by using the ACC for JLC threshold, which was proved by Picard-Zhang, and the special termination, we will get the termination of flips in this case. But here comes the point, is that if one wants to prove the special termination, we always want to do a junction to log canonical centers or log canonical places. But in this case, we have a Journalist pair. And after we do a junction, we will get a jungless pair rather than a usual pair. And therefore, we need the special termination actually for jungless log-canonical jungless pairs. And this is why the MMP for jungless pairs is important. So in the next part of the talk, I will just talk about our progress towards the minimal program for jungless pairs. So as a starting point, let's just review the classical minimal program. So that what I think about what are the troubles in the minimal program for jungless pairs. So here is just a brief summary of the classical minimal program. So we always start with a Q factorial normal projective over X with at worst log-canonical singularities. And we want to run MMP for some R divided D on X. Here in the usual case, this D equal to Kx or Kx plus B for some log-canonical pair XB. But I mean, for the jungless pair case, it will be like Kx plus B plus Mx. So if this naff, then we are happy. We already reached a minimal model and we are done. But if this is not naff, then we want to contract a D negative extreme array. And we need to prove that such contraction exists. And in that case, we need the cone and contraction theorems. So let's say we already have the cone and contraction theorems. Then this contraction exists, and there are three situations. We may reach a Mori fiber space, or a divisorial contraction, or a flipping contraction. For the first case, we are done. For the second case, well, that's quite simple. We can just replace X with C and continue. But if F is a flipping contraction, it is complicated, and we need the existence of flips. And finally, in all these situations, we need to apply the cone and contraction theorems again to preserve the Q factoriality condition of X. So once we have step 1 and step 2, we can say that, well, we can always run a D minimal program. But I mean, we still lack of the last part is that we want any of these steps will terminate. So the third part is on the termination of flips, which says that, well, if any sequence of these D flips terminates, then we will eventually get a bidirectional map, X to X prime, such that D prime is nav, or such that D prime is nav, or I mean, maybe I should write that here, or we will get like a Mori fiber space. Maybe I should write that here, but anyway. And anyway, so we will reach either step 0 or the Mori fiber space case in step 2, and we are done. So anyway, as you can see, to complete the minimal program, one needs these three parts: the cone and contraction theorems, the existence of flips, and the termination of flips. So for usual pairs and varieties with at worst log-canonical singularities, the difficult part is actually the termination of flips, because the first two parts are completely known. So like the cone and contraction theorems for the KLD case were proven in these three papers. The log-canonical case were proven by Ambro and Fujino. And for the second part, the existence of flips for KLD pairs, this is a well-known paper by Picard, Cassini, Hicken, and McKernan. And the log-canonical case was proven by Picard and Hicken Xu independently. And I also want to emphasize that Hashizumi has later given like an alternative proof. So maybe I should write that here. But anyway, so again, the difficult part for the log-canonical case is definitely 3, the termination of flips. So we all know the termination of flips in full generality in dimension less or equal to 3. But on the other hand, we know many special cases in dimension 4. So one of the most important case is the case when we have a pseudo-effective canonical divisor. And there are also many other special cases, and I will not list out there. But on the other hand, for Jonas pairs, the situation was completely different. So let's say we still want to run a DMMP, where the D is equal to K for B plus MX is the canonical divisor of a projective JLCJ pair. The relative case is also similar. So we know almost as much termination of flips as the pair case. Because so we know the case when dimension of X is less or equal to 3, or when the dimension is equal to 4, and this case for B plus MX is pseudo-effective. So I mean, so they are parallel to the cases for varieties and usual pairs. However, so also these three theorems, the Kuhn theorem, contraction theorem, and existence of flips, were unknown in general, even in dimension 3. So they are conjectured in this paper of Jingjun Han and Zhan Li, and they are re-emphasized in a recent survey of Picard. So we know the case when this XBM is Jonas KRT. So this is good news, but this is actually because we can find a KRT pair after we perturb the Jonas pair with an ample R divisor. And in this case, like all these three theorems will be immediately consequences of the usual KRT pair case. But on the other hand, for Jonas log canonical Jonas pairs, we may not be able to find such delta. So this is actually a key issue. But anyway, in my recent work with Heiken, we prove all these three theorems in full generality in any dimension. And in particular, we can show that we can run the MMP for any Q factorial JLCJ pair. So when I say we can run MMP, I do not guarantee termination, but at least we can run. So more precisely, so given a Q factorial JLCJ pair, we know the following. So first is the Kuhn and contraction theorem is that we can contract any K plus B plus MX negative extreme array. The second is the existence of flips, which says for any flipping contraction, the flip exists. And of course, we want to guarantee the Q factoriality when we run the minimum model program. This can actually be guaranteed by the Kuhn and contraction theorems, but actually we need to prove it separately. And as an immediate corollary, since we already know the termination of flips in dimension 3, by our theorem, we will complete the MMP for Q factorial JLCJ pairs in dimension 3, and of course, the pseudo-effective case in dimension 4. And also, we want to emphasize that we can run MMP with scaling. So this is actually another important type of MMP for any Q factorial JLCJ pair. So we can show that we can run MMP with scaling of any effective divisor. So once this KX plus B plus A plus MX is NAF, and this pair is JLC. And again, we cannot guarantee the termination here, but at least we can run. So in the rest of the talk, I will talk about like the details of our theorem. So our main theorem is assembled by three blocks: the Kuhn theorem, the contraction theorem, and the existence of flips. So first, I will list all these three theorems out. So our first block is the cone theorem. So what the cone theorem says? So let's say we start with a GLC J pair. And let us only consider all the negative integer arrays that are rational in the NE cone of X over U. Then we can write the NE cone of X over U into the positive part plus the sum of this rays, which means that the NE cone is spanned by the positive part and all these negative integer arrays that are rational. And in particular, so any such negative integer array will be rational. The second part is that if we twist by an ample divisor, then actually this RG left belong to a finite set. And in particular, this set of careful B plus MX negative integer arrays will be countable. And the third part says that we have a boundness on the length of integer arrays. So as you can see, so all the parts correspond to the standard cone theorem. We just replace K plus B with K plus B plus MX. So the second block is our contraction theorem. So this is we need a slightly technical assumption. Here we need to assume that this MX is Alcatel. So this is not for all JLC J pair. So once this MX is Alcatel, then we can contract any negative integer array, and we will get a contraction. And moreover, for any line bundle on X that is numerically trivial over Y, one always know that it is a pullback of a line bundle on the base. So so this assumption, MX is Alcatel, so this is a technical but natural assumption, because when running the MMP, we always want this X to be Q factorial. And on Q factorial varieties, MX is automatically Alcatel. The last block is the existence of flips. And similarly, we also need to assume that MX is Alcatel. And in this case, what we know is that once we have a flipping contraction, we will always have a flip. And moreover, if X is Q factorial, we will know that X plus is also Q factorial, and their Picard number are the same. So this will guarantee that there will not be infinitely many divisorial contractions in the MMP, because divisorial contractions will always decrease the Picard number. But it is possible that for non-Q factorial MMP, that the Picard number may increase. But here, we can prove that the Picard number will always be non-increasing, and therefore there will not be infinitely many divisorial contractions in any MMP. So in the following, I will provide some ideas of the proof of these theorems. So some of these ideas are expected to have important applications. So let's have a starting point, and let's assess the starting point at the existence of flips. So usually, if you want to show the existence of flips for a flipping contraction, it actually can be visualized as to find an ample model of the corresponding divisor. And ample model, this is actually that we want to show the existence of a good mean model for this divisor. So this is actually the philosophy when one wants to prove the existence of flips for the KLC case and the LC case. So for the unipair case, the existence of a good mean model is actually expected. And this is actually a special case of the abundance conjecture. However, for general pairs, we have a so-called generalized abundance conjecture, but this is false even in dimension 1. So with this very simple example, so let's say we start with x as an elliptic curve, boundary be 0, modular part mx is a non-torsion numerical trivial divisor. Then in this case, kx for b plus mx is numerically trivial, but not ordinarily 0. So clearly it is not semi-ample. And therefore, we need to, so this generalized abundance conjecture clearly is false, which means that not all generalized pairs will have good mean model. But to show the existence of flips, a generalized pair must have a good mean model. So therefore, we clearly want to use more properties of the flipping contraction and show that the good mean model exists for some special cases. So now let's look into the flipping contraction structure more in detail. So we start with the flipping contraction and a flipping curve C. Then there are two possibilities. The first case is when mx intersects C is non-negative. And of course, this is important that we do need the fact that mx is arc-Cartesian here, we cannot define such intersection numbers. So in this case, since mx.c is greater or equal to 0, we know that this x to c is also a kx to b flipping contraction. But xb is a log canonical pair, so the existence of flip is well known, and we're done. And the second case is that it's possible that mx.c is less than 0. And in this case, a key observation is that we can slightly perturb this m. And then m will not contribute to the generalized log canonical locus of xbm. And in this case, the next theorem is actually a very important observation, which shows that we do have a good mean model for some special cases. So this is also proven in our paper, which says, let's say we have a generalized LC G pair and over U. And let's say U0 is a non-empty open subset on the base. Then if the restriction over U0 has a good mean model, and if all the generalized log canonical centers of the generalized pair intersects x0, and finally we have this third condition, this very strict condition on M, which literally says that M is just 0 over U0. Then we can show that the original generalized pair, xbm over U, has a good mean model. So in the paper of Hikenshu and in another way by Hashizumi, they prove this theorem when this modular part M equals to 0. So for our theorem, so one can easily find that the last condition, this M0 descends to X0 and it is trivial over U0. So this seems to be a very strong condition, and actually it is. But one important note is that for the flipping contraction, because any flipping contraction will be birational, and M will be automatically generically trivial over Z, and therefore it's not so hard for us to find such U0 and let M satisfying the last condition. But we definitely we definitely need the fact that mx.c is less than 0 because we are doing the things over Z. But this will not be a trouble. But anyway, in this case, we will be able to apply our theorem to this flipping contraction. And on the other hand, since the abundance for Jonas pairs fails in general, it is actually not so surprising that we have to add such a strong condition to prove the existence of such special good minimal models. So, I mean, actually, with our third condition, this Jonas pair will behave actually very similar to a pair. So, I mean, we can do some tricks on the perturbation of the coefficients of the divisor of b plus mx, and in some cases, we will be able to actually get a log canonical pair structure. And in this case, many results for pairs in this situation, including our theorem, can be proven by using the same analog of the usual pair case. And it also turns out that this theorem is not only useful in the proof of the existence of flips, but they'll also be useful in the proof of the contraction theorem. So with the help of this existence of special good minimal models, so that's definitely one of the key points of the ideas of our paper, we will use the following philosophy to prove our main theorems. So first, we will prove the contraction theorem by using the Kohn theorem and the existence of special good minimal models. So more precisely, the Kohn theorem will guarantee that any negative extreme array is rational in the Kohn. And the existence of a special good minimal model can be applied when we need to construct a special birational model of X which satisfies some certain good properties. And we will prove the existence of flips by applying the contraction theorem and also the existence of such special good minimal models. And also the comparison of those Picard numbers and the Q-factoriality of the varieties under the MMP will be preserved by the contraction theorem. So we still left to give some ideas of the proof of the Kohn theorem, and I will pick this out and emphasize it. So comparing to the existence of flips, so the proof of the Kohn theorem is actually more tricky because we cannot use the nice structure of flipping contractions. Nevertheless, we can have we already have the following Kohn theorem for pairs that may not be log canonical. So this is proven by Ambrose and Fujino by using the theory of quasi-log canonical schemes. So I will not emphasize that theory at this point, but anyway, we have this theorem, this Kohn theorem for not necessarily healthy pairs. So what this Kohn theorem says? This Kohn theorem says that, let's say we have a pair which is not necessarily LC. Then the AE core of this pair is spanned by the positive part twisted by an ample divisor, plus the AE core which on the non-log canonical locus, and finally plus finally many negative extreme arrays. So it is usually not so easy for us to apply this Kohn theorem because we usually lack of information on the negative extreme arrays in the non-LC locus of this pair X delta. However, so a key observation is that for any JLCJ pair and ample divisor A, we can like plus A to the subboundary B plus MX and get some effective divisor delta. So in this case, X delta may not be canonical anymore. However, the non-canonical locus can be equal to the generalized canonical locus of the generalized pair. And therefore, so any ray in this equal at the non-LC locus of X delta will be contained in a GLC center of XBM. And let's say its normalization is C. And at this point, so this is like the most important part, is that we can apply a sub-adjunction formula for J pairs, which is a generalization of Kalmata's sub-adjunction formula, which was proven by Jingjun Han and Wenfei Liu in 2019. It actually says that if we have a generalized LC J pair, and let's say we have a generalized LC center, then we can do sub-adjunction to that generalized LC center and still get a generalized LC pair. And by using this formula, so after we do sub-adjunction to the normalization of the generalized LC centers, we will still get generalized LC pairs. And we twist it by A, but after we do sub-adjunction, it is still ample. The ampleness of A will always be kept. And therefore, we now can prove the Kohn theorem by applying induction on dimension. And this is actually the most important part. So let me, I guess I still have 10 minutes, and now I guess I think I have already finished the talk on the ideas of all our main theorem, but I still want to emphasize this induction on dimensions for generalized pairs. So here, I mean, the induction on dimension for generalized pairs by using the sub-adjunction formula in our proofs is actually the first time in the literature in the proof of any bidirectional geometry theorem. So this is actually an important philosophy in bidirectional geometry, because many fundamental results, such as the proof of BCHM, the proof of the BAB, and the proof of the ACC for non-canonical threshold, I mean, they all need induction on dimensions. So in the traditional case, if we only restrict ourselves to the category of pairs, then in general, there are only two ways for us to apply induction on dimension. So we either do adjunction to a prime divisor, or we do adjunction to a general fiber of some contraction, like a Mori fiber space. But on the other hand, like the canonical bundle formula and the sub-adjunction formula, so they will also decrease the dimension of varieties. But I mean, if you want to apply them for pairs, a key trouble is that we will get a generalized pair downstairs. I mean, a generalized pairs in the varieties with lower dimensions rather than a pair. And that will cause induction on dimension fails. But if we consider generalized pairs, such induction on dimension will work quite well. So, like for generalized pairs, we also have like the Ambrose Prokhorov type canonical bundle formula, and also the sub-adjunction formula, as I mentioned earlier. So I already talked about this sub-adjunction formula, so I will just briefly talk about this canonical bundle formula, which just says that, well, if we have a generalized LC pair instead of an LC pair above, and let's say this generalized pair is triple over the base, then we will also have a generalized pair downstairs, such that the generalized pair upstairs are linearly equivalent to the pullback of the generalized pair downstairs. And also, the similarities will be kept very well. So also, besides the generalized canonical bond formula and the generalized subadjunction, so generalized pairs also behave well on the usual adjunction to prime divisors, and also the adjunction to general fibers of contractions like Morley fiber spaces. But anyway, so because of this, so we do expect that our philosophy on induction on dimensions using the generalized canonical bond formula or the generalized sub-adjunction formula will be useful in the future, especially in the proof of some big conjectures like the Maclaurin-Shawcroft conjecture and Shawcroft's effective B-stem eminence conjecture. So for these two conjectures, we can see that they will always have a natural canonical bond formula structure in these situations. All right, so here is about the induction on dimension. And in the end, I will talk about some open questions which are related to our results. So the first question is that, can we drop the MS arc-arterial assumption in some of our main theorems? So, I mean, we do not need the assumption, we do not need this assumption in the Kohn theorem and the theorem on special good linear models. But we do need this in the contraction theorem and the existence of flips, because we need to consider the intersection numbers of MX with curves. But so I mean, so I suppose that this is only for the completeness of the theorems. But I mean, if we only focus on running the MMP, we don't need to care about this. The second is that, can we prove a stronger version of the theorem, of our theorem on these special good linear models? So this theorem can already be applied to the proof of existence of flips. But as I mentioned, the third condition seems to be quite strong. So we are wondering if we can replace this condition with some weaker assumptions. And finally, this is actually a more general question. So we want to see that, so what additional conditions do we need to add for this modular part or for the boundary part so that the generalized abundance will be expected to hold? So clearly, the extreme cases, if M is 0, it is definitely expected because it is just the abundance conjecture. For arbitrary M, it is clearly wrong, even in dimension 1. So one may want to find some kind of proper middle condition. So yeah, I think in the last day of last year, has been proved the non-vanishing theorem when this modular part M contains an ample divisor. And this might be one condition that we want to look into. All right, so I think I'm almost out of time, so maybe I'll just stop here and thank you for listening.
Thank you very much.
So any question for the audience? So then let me ask a simple naive question. So for the generalized pair, the abundance is not true. So can we say instead of K plus boundary plus the nef, you add a peak 0, you add some topologically trivial part, you can make it abundant?
So what do you mean as some topologically trivial part?
So instead of this log canonical divide to be semi-ample, say you add a peak 0 to make it semi-ample. So
well, I mean, so I'm not quite sure. I mean, like for the generalized abundance. I mean, so that says that. So like for this question, I just ask that when will this kx plus b plus mx to be
semi-ample.
yeah, to make it ample. But so I mean, this is clearly not true, but I mean, there is a similar conjecture which was proposed by Lazig and Peter Nell. So what's the conjecture is the following. So we still have such John-like pairs, but we assume that mx is NAF. So M is not a NAF B divisor. I mean, M is actually a NAF divisor. And I think they want to additionally assume that kx plus b is pseudo-effective.
I see.
And in that case, they want to ask whether kx plus b plus mx is numerically semi-ample.
I see.
So I mean, so my feeling is that like all the things which are related to this generalized abundance seems to be very tricky.
Okay.
For example, I mean, even if we only consider the numerical generalized abundance, we want to assume that kx plus b is pseudo-effective. Otherwise, there will be counter examples in dimension 2.
I see. So thanks. Audience, any question to Jihao? So we are running out of time, but let me ask one more. So you use induction. Does that mean your result recover the pure case, the case where the NEF part does not appear?
No. I mean, like we need this theorem. So our proof will rely on this theorem of Ambrose and Fusino. And when the moving part is 0, and we have a log canonical pair, then this part will just be 0. And I mean, that will just proved by Fusino.
I see. Okay, thanks. I guess if no audience, I guess that the next talk is 15 minutes away, right? So I guess Yongkai will take over, right? Okay, thank you so much to the speaker. Thanks.
Okay.
Thank you.
Yeah. So we'll take a 15 minutes break.
Okay. So Yongkai take over. Yeah. Thanks. Okay.
Yes.
Thanks, Jihao. Yeah. Okay.